Hello Chem 1A, this is Chapter 2, Lecture Video 4, and this is our last lecture video for the chapter. We're going to be talking about atomic weight in this lecture video. Now, if we have just a lump of carbon atoms, some of those carbon atoms will be carbon 12, some of them will be carbon 13, and some of them will be carbon 14, as these are the different isotopes of carbon. Now, there will be different percentages of each isotope present. Generally, most elements have one isotope that's way more stable than the rest, so there is a lot more of a percentage of that element. For instance, in this case, carbon 12 is the most stable isotope of carbon, so it's going to probably be roughly 98 to 99% of the carbon atoms will have a mass number of 12. Well, this kind of creates a little bit of a problem when we talk about the mass of an atom, because depending on which isotope that element is, it's going to have a different mass, right? This is the mass number 12. This is the mass number 13. These are going to be slightly different from each other. Now, again, these mass numbers are approximated just by adding numbers of protons and neutrons together. The real numbers are slightly different. They're not integer values. But nonetheless, they'll still be different from each other. So this brings us to percent abundance. Now, we're never going to really use this formula here. This is just a regular percentage formula. But the percent abundance of an isotope is just simply the number of atoms of that isotope divided by the total number of atoms of that element times 100. In other words, the part over the whole, which is times 100, which is basically every percentage ever calculated. Atomic weight is really a weighted average. And so it's not just your regular average. We're not just averaging 12 and 13 and getting 12.5. It's not that simple, because at the end of the day, carbon 12, like I said, 98% of carbon atoms are going to be carbon 12. So to treat both 12 and 13 as equal components is not very accurate, right? Because most atoms are going to have carbon 12 as the isotope. So what we do is we use a weighted average, and we weight the mass based on the percent abundance of each isotope. And the way we calculate that is that our atomic weight is equal to our percent abundance of isotope 1 divided by 100 times the mass of that isotope. Then we add this to the second isotope, but again, we're going to use the percent abundance of isotope 2 divided by 100 times the mass of isotope 2. And if we have 3 isotopes, we're going to do this again. And if we have 5 isotopes, we have to do it 5 times. With the percent abundance for each isotope and each mass multiplied together and then added together as a whole. And this is a weighted average. I will give you this equation on the test. You do not need to memorize it, but you do need to know how to use it to do calculations. So let's do some example problems. So we're told that naturally occurring chlorine is 75.53%, chlorine 35. Which has an atomic mass of 34.96885 atomic mass units, and 24.47% chlorine 37, which has an atomic mass of 36.96590 atomic mass units. And we want to calculate the average atomic mass, or in other words known as the atomic weight, of chlorine. Well, if we just utilize our equation here, we know the atomic weight is equal to, I can spell weight, I swear, is equal to the percent abundance of, we'll just call this one isotope 1, so 75.53 divided by 100 times the mass of that isotope, 34.96885 atomic mass units, plus 24.47 divided by 100 times the atomic mass of that other one, 36.96590 atomic mass units. Now, if we're doing this calculation, we can just plug this into our calculator and enter. However, we'll lose information about how to determine the correct number of significant figures. So let's break these down into two parts, right? I'm going to calculate these values here and these values here to get what they multiply out to, and then we'll add those two values together. And this way we can see what our sig figs are going to be. Okay, so after calculating these, we can see that our first number is 26.412 atomic mass units, and then the other number is 9.04556 atomic mass units. Now, if we look at our numbers here, this number here has 4 sig figs. This number here has 1, 2, 3, 4, 5, 6, 7 sig figs. So when we multiply these two numbers together, we should only get a number that's actually 4 sig figs. Now again, I'm not going to round until the end. I'm just going to circle it to say, hey, this circled number is my last significant digit. Over here we have 4 sig figs with this number, and again 1, 2, 3, 4, 5, 6, 7 sig figs here. So this number should also have 4 sig figs, which means I'm circling this number here. Now I can add these two values together to get my answer, which gives me this value, 35.4575 atomic mass units. Now if we look at our numbers that we added up above though, this one is to the hundredths place, and this one's to the thousands place. This means I need to round to the hundredths place, giving my answer as 35.46 atomic mass units. Now in this problem, we can actually compare this to the actual value on the periodic table for chlorine, and we're really close. It's like 35.45 if you look at the periodic table, so this is pretty dang good. I wouldn't ask this problem as written on a test because of the fact that I'm telling you that it's chlorine. And at the end of the day, the average atomic mass is what's in the periodic table square for chlorine. So I wouldn't be asking you to solve for it because you're always going to have a periodic table given to you during the exam. I might say, hey, naturally occurring element X has these numbers, and then that way I can make this problem into a testable one. So let's do a slightly more difficult problem, and then we'll end this chapter. What are the percent abundances of the two isotopes of bromine if the isotopic mass for bromine is 79 is 78.9183 and bromine 81 is 80.9163 atomic mass units? Now, in order to do this problem, the first thing we need to do is we need to look up the average atomic mass of bromine from the periodic table, which we get 79.0904. That looks like a U. AMU. All right, I know that atomic weight is equal to percent of ISO 1 divided by 100 times mass of isotope 1 plus percent of isotope 2 divided by 100 times mass of isotope 2. Now, we actually have the masses here given to us in the problem. We have this number, and we have this number, and we have the atomic weight that we looked up from the periodic table. This still is an issue, though, because we still have two unknown values that we have yet to be able to solve for. And if we only have one equation, we can't solve for two unknowns. So we have to be able to develop another equation here that'll allow us to isolate one of these unknown variables. Now, the way to do this is to understand how percentage works. There are only two isotopes of bromine, so this tells me that the percent of isotope 1 plus the percent of isotope 2 has to equal 100%, because we know all the percentages added together always has to add up to 100. This gives me an equation that I can now use to isolate one of my unknown variables. Right? So if I take this and go, okay, percent of isotope 1 is equal to 100 minus the percent of isotope 2, I can plug this in for that, for isotope 1. And now I have I have changed an unknown variable into the same unknown variable that I have already in the equation, meaning now I only have one unknown that I can solve for. So let's plug this all in, right? So I have 79.904 atomic mass units. That's the average atomic weight. I have 100 minus isotope percent 2 divided by 100 times, and this again is isotope 1. I'm going to say the isotope 1 is 79, so 78.9183 atomic mass units, or AMU, plus percent of isotope 2 over 100 times the other isotopic mass, 80.9163 AMU. All right, so if we look at this, then I have one unknown variable, it's isotope 2, and now it's pretty much algebra. So I need to factor out 1 over 100 here, and then I'm going to multiply both sides by 100 to get rid of it. So I'm going to take this and multiply by 100. This will give me that 7990.4 is equal to 7891.83 minus 78.9183 times isotope 2%, and we'll just use a different color here, plus just 80.9163% isotope 2. Right. So at this point, we can kind of rearrange a little bit. I'm going to combine like variables. I'm going to move this guy over here by subtraction, and I'm going to add these two numbers together, and this will get me closer to the answer. Okay, so after simplifying, this is the equation that I get, and now I can just divide both sides by the 1.998 to get my percentage of isotope 2, or in other words, BR 81. And this gives me 49.33%. I can then just take this value here and plug it in back into this equation here. Whoops, sorry. There we go. And get my percent of bromine 79. Sorry, there's a lot of space here. So we know our percentage of isotope 1 is basically equal to 100 minus 49.33. So this gives me 50.67%. So just to kind of clear everything up, BR 79 has our percentage of 50.67%, whereas BR 81 is 49.33%. All right. As always, if you have any questions, please don't hesitate to contact me via email or office hours. I'm always happy to help you guys.